So good afternoon. So I will be dealing with hash-based digital signatures. How my interest has stemmed is because post-quantum cryptography has come. So existing signatures, using RSA and ECC, ECDSA, may be ineffective after maybe 5 or 6 years. So that's why we are ready. We should be ready for post-quantum signatures. So NIST has called for competition, and finally, I will advance it. Finally, they have selected one algorithm for something known as KEM, that is key encapsulation module, and 3 for signatures. So 2 are based on one problem, mathematical difficult problem known as ring learning with errors, and the other one is based on hash-based digital signatures. So I will be dealing with this now. Next one. So here, it actually, this is a very old idea that was presented, around maybe some 50 years ago by one person known as Lamport. So what he has told is this, suppose, you want to sign a message, that is 256-bit message, that message is a hash of something else. Suppose you want to sign, what he told is select 512 random numbers, that 256-bit random numbers. So I have shown you first top line, 256 random numbers, and then bottom line another 250 random numbers. Now, suppose your message is 0110, something like that. If bit is 0, you select it from this top one. If the bit is 1, you select from the bottom one. So that means, what you are doing is you are collecting 256 bit words, one from top, one from bottom, depending on whether it is 1 or 0. So that is signature now. Now that means, your signature unfortunately is very large now, because it is 256 into 32 bytes. So that is very large. Okay, and your storage also is large. So next, what happened was, there is one intelligent fellow by the name of Internet. So the Internet has totally revolutionized the complete hash-based digital signatures. What he told is, instead of taking 1 bit, why don't you take some log W bits? That is, suppose W is 16, I will take 4 bits. That means the hash I will take 4 bits at a time, and then I will do some operation, like suppose that my word is say 3. I will hash the word 3 times. And then like that, depending on that 3-bit word or 4-bit word, I can hash it as many number of times as possible. So that hashed one I will send it. Whereas, the public key generation, what we do is, we hash it to the full speech. So suppose W is, I told you 16, I have to hash 16 times, and that I will store. So public key is 16 times hashed version of all your 64 private keys. But unfortunately, or fortunately, the hash is not reversible. So that's why they thought it is secure. But as many of us are aware, some of these software like PDF and all, they use something on hash chains. That means 1 lakh times, people hash. So maybe, if you have some knowledge of that, that can be perhaps broken. So that's why what they have introduced is, instead of directly hashing, why don't you just in between do some operation? That I think is the next slide. In addition, what you have to do, suppose somebody wants to forward the message now. He has recorded your one signature. Now what he can do is, he knows maybe this some repeated hashing of that may lead to some other signature. So that's why what we do is, we introduce one checksum also. So that means, if there are this, suppose 64 256-bit word, I have taken W16. That means 64 words are there. So the 64 words are L1. Then I will calculate something known as inverted checksum. That means that value I will take, complement of that with reference to 15 I take, and add all of them, and that will form another few bytes. So for example, for this case, this I have given example W2 N256. Originally you have 128 this log W bit words. Additionally, we are getting 5 bits. So 133 bit words are there. So now the advantage is, if somebody wants to tamper with your this message, what happens, signature, then what happens is this checksum will change. That is because that is also encrypted and sent, so that will change. So because of that, we can know that some forgery has occurred. So this was one of the pioneering ideas of Internet. Then this actually, is the operation done. That means it is not just, repeated hashing. You have to add some randomness to that. So this randomness, you have to periodically generate using this, that is, using something known as some temporary information also. That is, at what step you are doing, something like that. Because, this some receiver should know where, what random number is generated and how. So this random number is generated based on other fields like, public seed and one-time signature and address. That is what called address. So now this is supposed to be secure. That means it is not continuous hashing of a word, but in between we are doing some operations now. But because this overhead comes, suppose I want to hash it, this let us say 16 times, I have to do extra generation of 32 random. This PRF means pseudo random function. 32 times I have to invoke that. Then I have to get that exclusive OR, and then only I can hash. So that means this definitely has to overhead, but it has to this security. So now, this, unfortunately, this is called one-time signature. One-time signature means, suppose, only one message I can send using one public key and private key that is generated. But now, the practical is of not much use, because I want to send, let us say, some number of messages. So that's why, what they have done is, they say we should use a Merkle tree. Merkle tree, many of you must be familiar in some of the applications like blockchain and all that. So here what we do is, this we can build some top one Merkle tree. So Merkle tree, what happens is, I need not verify all the public keys. I only verify the root. But I should tell the authentication path from the starting point to this one. So for that what we need is, we have to, for example, suppose this is my selected point. How to go there? I should say, please go, take this. If I take this, I go here. Then I will say take this. Then I go here. So that means, you should know that path. There are many efficient algorithms for computing this authentication path. So that means, what receiver I have to send is signature of the message plus authentication path. So this is what is the signature. But this again, is troublesome, because this, once you hash this, in this first layer, here, this layer, for example, when I got 16, I told 67 chains will be there. These are all the chains. 67 parallel chains are there. Now, this, that means, these words will be 67 into 32 bits. Okay, 67 into n bytes. So now, that, to handle hashing in the upper layers is very difficult. So that's why, this particular standard known as XMSS, this RFC. So there they have told, use one compression tree known as L tree. So this L tree, what it does is, that is before Merkle tree, one more tree is there. This tree will take those big words and compress all to just n bytes. That is n number of 32 bytes. So this is how this XMS. But unfortunately, application is limited, because it is again, even though number of users can send number of messages, each one message, but still, this is supposed to be not very advantageous. So that's why, today, another contemporary of this has come, known as LMS, that is Leighton-Michaeli scheme. The Leighton-Michaeli scheme also more or less similar. Only thing is, you will not have this compression tree. Instead, what he says is, take all those 67 bytes, so many in internet chains, and then you can hash all of them together. Then also you get n32 bytes. So that means this state is missing in LMS. Okay? But again, same thing is OTS. So next generation, now we have come to post-quantum signature known as Sphinx. No, these are all the operations I was mentioning. That means everywhere you have to generate this. It is not just combining two means. Normally, what we think is we pad those two and then we hash. But it's not like that. Before padding, you have to actually mix it with some exclusive OR with some two random generated numbers, and that you have to do. Okay, so this is the overhead for that. So next, Sphinx is the latest one. So the very expansion of Sphinx is stateless, practical, hash-based, incredibly nice. Of course, any other can say all those things, but it is really so. But a lot of disadvantages also are there. So now, this is practical, stateless. Stateless means Earlier one what I have seen is, if I know I have used this, suppose XMS you see, if I know I have already used this, I cannot use, I have to remember, I have used that first pair, then I have to go to second pair. That is what I meant by stateful. So now the Sphinx, the beauty is, it is stateless. That means you need not bother about what you have done before. Okay, so this one is, I will just show here you see, very complicated in the sense that he uses in the bottom layer something known as a forest tree, forest of random sets, and afterwards he uses Watt's chain and Watt's that top layer Merkle tree. Then like this there are so many trees. For example, the height of the tree is known as H, and there are D layers there. So that means massive computation you have to do. But the beauty here is the root it takes to the top, root means ROUT, root, it takes to the root of this tree is completely random. That means that is only decided by the message, and then that's why what he calls it as verifiable this one. But beauty is this public key size is very small. It's just hardly some 64 bytes. So that means this is outgrowth of the previous ones, which were only this one-time message system. So here you can see this security parameter is that number of bytes, and then height of the tree, then number of layers, and all layers are similar, and then number of trees in FORS. FORS is forest of random sets. I will just show you one slide where what it does is, you see this is known as forest of random sets. So here what you do is, suppose I have this some operations are there. Suppose some message finally you get. That message will select one of the elements here, because this is actually this kt number of n byte. There are k such blocks. Each is having t n byte 1. T is very large. T is 2 power d. Okay. So that means this what you are selecting here is decided totally by your there is one formula. Now you see here what it says is, suppose your message is I have got an example here K6A3. You have got 18-bit word, let us say. First one is 3 bits are 100. I will say you select this. So from here Merkle tree I have to define. So I go to that root. So second one is 2. So that means this is 0, 1, 2. So third one is 3. So that means here each of these k trees and k roots I have to define. Automatically that will define. So that will decide what are all these individual roots here, and these are hashed together. So this is very complicated, because everywhere number of layers you have increased, so number of roots have increased, and here number of k itself is large. That is in the actual thick scenario it will be 12 or something. So that means the key size has become extraordinarily large, and there is this methodology. This is finally he gives you some simple and fast implementation. Simple means that chaining function I have shown you, random numbers are not exclusive ordered. So that is simple. That means security level is low. F means it is very robust. So this one he has given various parameters are there, and depending on your NIST security level, this 1 to 5 they have defined. Okay. So fifth one you see very large signature size. So 49 kilobytes is there. Okay, signature size. But one point I would like to tell, maybe this is the last one. CA designers now this is all signature size is very large and the security level is 5. Already I have told. Now you see NIST final statement is this: if NIST confidence is in better performing signature algorithms is shaken by new analysis, Sphinx could provide an immediately available algorithm for standardization. The reason is, you see, there was an isogeny based key exchange suggested in post quantum computation, and now it has withdrawn. 2 rounds it was there. The reason is somebody has found an attack. Because human brain is great, some invention may be there to say, now tomorrow this also may not be there. Now, the whole thing is based on security of SHA, SHA-3 or Sheikh or SHA-2. Suppose somebody this finds a collision for SHA-3 tomorrow, then what we should not say sink the whole thing. So what we have done, that is why Sphinx is a framework. Tomorrow if new hash algorithm comes, I can simply substitute that hash algorithm in this. Okay, but the price you have to pay is this signature size is very large. So now what one point I want to tell is this CS should have better, that is more key size than the users. For example, RSA you can say 2048-bit key this should be there for this CA, and 1024 they allow for the public. Similarly here, maybe level 5 we have to use for CA, and maybe level 3 you should use for the common. So these are all the decisions that have to be taken. Thank you very much.